Okay. All right, so let's look at the N-body simulation. So you can click here to get to the files. I already have a tab open for that, and I'm going to just step back here. All right, so what you get is the N-body starter files, you get an FAQ, and you get the N-body simulation document. So let's just take a peek at the starter files. I think I went too far. Let me go back one. All right, so there's two folders in here. There's the regular starter code, and then there's optional N-body files. I didn't look into the optional files. You're welcome to do that. Oops. All right, so what you see in here are Java files. Let me put this in list order. So Java files, GIF files, and a TXT file. So the GIF files, of course, will be used to draw your universe with your planets, basically your solar system. There's 4 Java classes, and we'll look at those later, and there's a planets text file. So let's just look at that briefly. So this file is what you're going to read with your program, and you're going to use it to create 5 bodies. That would be 4 planets and a sun. So the first number, the 5, says that there's 5 bodies. That's where you get n bodies. N is the 5, n equals 5. The next number is the size of your universe. Basically, you're going to draw a star field, and then the planets are going to be in it. So the dimensions of that star field is what comes out of this number. Then each row represents a different planet or a different body. So this first row represents the Earth. The first 2 numbers are the X and the Y coordinates for the starting position. The next 2 are the X velocity and the Y velocity for the starting of the simulation. The next number is the mass, and then of course the image used to draw that planet. You can skip the last line in the file, you won't need this. So I just wanted to point out that these have an E in it with the little plus and equals. And this is written in scientific notation. You do not have to do anything special to parse this file. You can read 2.0 E plus 11 as a double. Just use your scanner to call next double and it can read it. What this means is 2.50 times 10 to the power of 11, in case you're wondering. Okay, so that's the files that you start with. We're going to backtrack to the lab. All right, the lab itself gives you a nice explanation of what to expect. So you're going to read in details of the universe. That's from the text file we looked at. Then you're going to simulate the universe. That's the part where you have to code it. So starting at time equals 0 and continuing delta time, this little triangle means delta means change in time. So each little step is a little time increment, and the time will go all the way up to capital T, the total runtime of the simulation. And then you're going to animate that. That's what the standard draw class is. You'll have 4 classes. The standard draw, which basically does all the drawing for you and you won't alter that class. The runner class, which creates the N-body simulation. The N-body simulation, which has an array of bodies. And then the body class itself, which determines the behavior of the body. All right, so we looked at the text file and the parts of it. This is a nice diagram to tell you how to read it. Then we have formulas for the force and the acceleration. So pairwise force means the gravitational force that one body imposes on the other. And we've got a nice formula here, and we've got some diagrams to determine that. So I'll come back to the formulas later. So this asks you to put all of the source code, the starter code, into your project. All those GIF files and the TXT file are going to go in the project folder, but not in your source code folder. So the body is made up of X and Y position for the planet, the starting velocity for that planet, the mass of the planet, and then it's got some extra fields. So every time we do a step in the simulation, we're going to calculate the new net force in the X direction and the Y direction. as well as the acceleration in the X direction and the Y direction. And of course, there's an image, so we know which picture to draw for each planet. The N-body simulation has an array of bodies. And then it's got some other details about the universe. So there's some tips on how to load that into your assignment. So you'll start with the body class. You'll create a constructor to initialize all those values that you found in the text file. You're going to want to write some getter methods for your private instance variables for X and Y and mass. And then here's where you start doing the mathematical methods. So I will come back to that in a minute. All right, I'm going to jump to the math because the rest of this, you just have to step through and follow the steps. All right, so let me switch to the math. All right, so actually, let me run the simulation so you can see what it looks like. Run, there we go. So we have the sun. This is not drawn to proportion because the sun would be a lot larger. But we see that the planets are rotating around the sun, and depending on their initial velocity and their distance, they will have different orbits. So this is what it should look like when things are all going well at the end. All right, just wanted you to see that. Okay, so let's talk about the math. Okay. All right, so in body simulation, we have these planets going around the sun. So I try to break it up into some steps here. So you want to calculate the distance to a body, then you want to calculate the force to that body, then you want to calculate the force in terms of its X component and its Y component, then you want to calculate the sum of all the X forces and all the Y forces. Remember, don't include yourself. And number 5, you want to update the things like acceleration, velocity, and position. So to solve the first one, calculating the distance to the body, not move that one. Here, I'm going to move this over here. Whoops. There we go. So this is going to be a private method in the body class. So you have this planet that's yourself. It's called this. And then you're trying to calculate your distance to other. And in order to do that, we have to use their current position. So we know the X and Y of ourselves, and we know the X and Y of the other planet. So here we create ourselves this little right triangle. And so if we can determine the difference in X and the difference in Y, we can use the Pythagorean theorem to solve for the distance, which is the hypotenuse. So let me write this as dx for delta x. So this is simply the other's x minus this x. And then of course, the delta y here, I'll label it. There you go. And dy is simply the other's y position minus my y position. And so the distance up here is the square root of the sum of the square of the distance in x and the distance in y. So that's your Pythagorean theorem. So notice that this method has a get in front of it. So this will return the distance. It doesn't set an instance variable. So I wanted to be really clear on that. All right, so that's step number 1. So let's go back to our list. We've calculated the distance to a body. Now we have to calculate the force between a body. So I'm going to pick up this this method and drag it down here to where I'm working on the force. Okay, so this method, again, it's going to return the pairwise force. So we're not trying to save it as an instance variable. So how do we calculate this force? Well, fortunately, we're given a formula. Do it from memory. The formula for force is given to us. That's the wrong pen. It's the gravitational constant G, which is actually in the class as a constant, times the mass of our planet, times the mass of the other planet, all divided by the distance between the two planets. So where would we get the distance? We simply call this method up here. Call this method anytime you want to get the distance between yourself and another body. So that's where the distance is going to come from. Of course, you can get your own mass and the mass of somebody else. So that's the formula for get pairwise force. All right, so the next step is to do number 3, which is calculate the force in the x direction and the force in the y direction. So let me grab that. These two methods will solve this problem. Again, notice that they have let me slide this over. They have the get in front of them. That means they return the force in the x direction and the y direction. They don't actually set it. So basically, we can use ratios to solve this problem. We have this right triangle for determining the force. So we know the force. We've been able to calculate the force between the two planets, and we have to break that into the x component and the y component right here. So if we can think of this as the same thing as basically our distance, and we have a dx here and a dy here, the proportion of the hypotenuse of these rectangles will be the proportion of the hypotenuse to a leg of these will be the same from one triangle to the next. So we can use that. So let me move this up here so I can show you my math. So we would say that Fx, the force in the x direction, is proportional to the whole force, just like the distance, the change in distance of the x is proportional to the entire distance. So we can multiply both sides by f. And of course, that would eliminate this one here. So Fx is equal to the force times the ratio of the change in x over the distance. So let me write this a little bit more succinctly right here. So it's the change in x times the force, and that capital F you can get by calling the pairwise force, divided by the distance, which you can get from calling get distance. And of course, that would be the change in y for determining the force in the y direction. All right, so that gets us to step 3. That finishes step 3. Now what we want to do for 4 is, now that we have ways to calculate the force in the x direction and the y direction for one body, we have to sum all of those for each of the bodies. So let's take the planet Earth. It has forces being acted upon it by Mercury, Venus, Mars, and the Sun. So we have to take all of the force in the x direction for each of those and sum it together, as well as the force in the y direction for each of those bodies and sum it together. So that would be the set net force. down here. And I'm just going to write this in English because this is really a loop. Now notice that this time it says set net force. And so these here are instance variables. So you're going to want to set these instance variables. Now, at first you want to set them equal to 0, okay? Because you want to start from scratch every time you do a step in the iteration. So just to write this in more like English, it's the sum of all, let's see, forces in the x direction of all bodies. And you can exclude yourself. You don't have to impose force on yourself. And of course, this is the sum of all forces in the y direction of all bodies. Now notice that you are getting an array here. So you have to iterate through that array of bodies, and for each body, go find out the force, then turn that into the force in the x direction, and then you can sum it here in this method. All right, so again, that's done with the loop. And lastly, we're to step 5. And step 5 is update instance variables for acceleration, velocity, and position. So I'm going to grab this last method, and we'll bring it over here. All right, so this last one is going to update all of the instance variables that you see here. So we're given the formula for acceleration, which is you're going to take the force and you're going to divide it by the mass. So we're going to take, let's get a real color. We're going to take the force in the x direction and divide it by the mass. You probably need to translate these into Java, but I'm just going to give you the formula. So the force in the y direction divided by the mass, and that's your own mass. And of course, let me just remind you that these are actually, this should be actually the variables that you're setting over here. What are they called? X net force. Okay. Divided by mass. All right, once you know your acceleration, you're going to calculate the velocity. The velocity is going to be the acceleration multiplied by how much time is elapsed. Now dt comes from the parameter. We're told how much time is elapsed. So that acceleration is applied over that amount of time. Now notice that we're doing plus equals. So acceleration increases the velocity or potentially decreases the velocity if it's negative. So the velocity shouldn't start at 0. It should start at the existing velocity and then increase in speed or decrease in speed based on acceleration. And then lastly, now that we know a velocity over a particular period of time, we just apply that over amount of time to change its position. So again, we're applying the velocity in the x and y direction over a particular period of time to find out where its new position is. Okay, so again, that's the steps that we went through. We calculated the distance between the bodies, which is used in several formulas, calculate the force between yourself and another body, break that into the force in the X direction and the force in the Y direction. Then you want to accumulate all the net force for the X direction and all the net force for the Y direction. And then ultimately you want to use that to update a body's acceleration during that time period, its velocity, and its change in position. All right, so that's the part that I wanted to go over today. I will turn off, actually, I'm going to reattach this.